So good morning, thanks for coming again today. And again, the information of the two seminars is over here if you need to check it. And so I'm going to describe the concept of equilibrium that we are going to use for this type of analysis, and then we will describe a little bit what we will do using equilibrium to understand better how electrical and gas systems interact. So this is the purpose of today. So let's go to see an equilibrium. So anyway, so this is a very simple problem. It's a linear objective function. We want to maximize this guy control the variable x, but depend also on y, okay? And this is a circle, so we want to maximize this linear function being inside this circle, right? And the black guy over here is trying to do the same thing. This is a circle as well. Move a little bit to the right. So this is a convex region, convex feasibility region. And we also try to maximize a linear function. So two pretty simple things, but there's no, in principle, easy way to solve that if you're not familiar with that, because this guy controls only x, but everything depends on x and y. And this guy controls only the y, but everything depends on x and y. So how this work? Which means basically this guy is trying to maximize over x, but is getting interference, is getting bothered by this other guy, and the other way around. And life is like that, by the way. So there is no such thing as an optimization problem. If you are using single optimization problem for your research, you are missing part of the pictures. Because if you do something, you are getting into trouble with somebody else, you are bothering somebody else and the other way around, it's always like that. So agents in a market, if I do something, I'm affecting what the competitor is trying to do. So this kind of framework is much more general, and I think is more closer to the real world than the single optimization problem, because we are all the time through our actions modifying what everybody else can do and the other way around. This is particularly true in market. So just the concept of equilibrium, we can do this in a little bit more general manner, but for me an equilibrium is this joint solution of two optimization problems or many optimization problems which are interrelated. So I cannot solve this one because I don't know the y. I cannot solve this one because I don't know the x. So I have to solve the two of them at the same time. And how can I do that? Okay? So that's the idea of equilibrium. Real world is like that, not optimization problem. Optimization problem is a particular case of this, which is very strange because it never happened. This is what is happening. Okay? I remember Professor Stein Wallace from Norway, that is an expert on optimization, you may know him well, said, well, deterministic problem, this is something that doesn't exist. Such things does not exist. I mean, you don't know the data. Whatever it is, you don't know the data. Even for very standard classical problem, if you want to build a bridge, you don't know the exact detail of the resistance of the material that you are using. You don't know the characteristic of the whatever material you are using for building the bridge. So you don't know the data. So everything is stochastic. So let me extend this a little bit. Everything is stochastic, of course, and everything is equilibrium, is not optimization problems, okay? Because you are always has the interference of somebody else. So sometimes we may decide, well, the influence of y over here is very small, so we may forget about the y effect over this problem. But in market, this is not usually the case. So this is what we are going to do, and this is the definition that we would do the problem. So let me go a little bit in case that you are not that familiar with that. So the blue problem is over here. We have this circle, which the center of this circle is 0. Very simple. The radius is 2, as we can see, 1 to 2. And we want to maximize this objective function. And we had to be inside the circle, but things change, everything changed for me according to the action of this problem, which is moving the y. Okay, so okay, and this problem is the black one, which we have the center over here in 1, 0, and again we have a radius of 1, and this objective function, linear objective function over here. So let's look at the, let's assume that the x problem can actually move both of them. The x problem can control x and y, okay? Has control over the two variables. This is not the case in real world, but if this is the case, what we want is to be inside the circle, the blue one, and we want to maximize this objective function, the blue lines at the contour of this particular line, which are, we have the slope, as you can see, is -1, okay? So, so we have this kind of thing. So the optimal solution will be somewhere over here, 1 something, and over here 1 something as well, okay? So this is the optimization, provide that, let's say the y problem surrender control, and this is the guy that solved the problem with everything, which is not what we want to do. So the solution is over here. Let's do the opposite thing. If we now assume that the y problem is the one controlling everything, okay, is controlling the y and the x, then we have the optimization of this problem. This linear function that we have here, this is the contour plot of this linear function that we have, okay, which is the slope is just 1. Okay, and we have to be inside the black circle, right? So if we want to move in that direction, it's increasing in that direction that way. So the solution will be somewhere over here, minus 0.45, something like that. That over here is not far away, probably 1 point something. So that will be the solution, okay? So, but the y problem does not control x and the other way around. So what we can do, let's go a little bit in detail over here. So let's assume that we parameterize the solution of this is the x problem, the one on the left-hand side, the x problem. And let's see that we want to get solution parameterizing for different values of y. So that's a way to somehow get the solution of this problem as a function of the options of the other problem. So let's say that the other problem, the y problem, fix the y, and then we optimize for this fixed y. And we want to look all the possibilities in that direction, right? So this one, we get this. So if the y is fixed, means that we have to move, this x problem has to move on a horizontal line, right, at the y1 level, or y2 level, or y3 level. This is what to do. Since we want to move as far away inside this circle, the solution will follow this pattern. This is what is going to happen, right? Okay? Simple things, but please follow me in this case, because we will do more complicated things later on. Okay? The same thing for the y problem. For if we fix the x, I'm fixing x here. So the x is moving in that direction. Different values of x, vertical lines, if we fix the x, right? And then, so we fix the x and solve the problem for the y. Since the y we want to go in the right-hand side circle, is this circle, and one had to be, the objective function is this with a positive slope. So we want to go as far away in that direction. So we are gonna get is different point moving in that direction, right? So if we actually do the two things together, so one fighting against the other, eventually will settle down in an interesting point, right? Which is this point, right? And this point is what we call an equilibrium in this problem. This point is interesting. We will see now is equilibrium in the Nash sense. So if, let's say, the x problem doesn't change anything, the y problem doesn't want to change anything. So the optimal solution in this point, we fix the optimality condition of both problems given the value of the other problem. So if we fix y to its value, then and solve the x problem, we don't move. We get just the same x, and the same way with the y. This is the definition of equilibrium, Nash equilibrium in that sense. Okay, so so this a little bit of graphical thing. Let's do let's look at that from the more analytical point of view, which is a good idea after we have geometrical signs sometime in many problems. So this is the problem for the x. I just changed a little bit things to make it in standard form. This is less than or equal to, and I want to minimize, because I prefer minimization, and then the same thing for the second one. I want to minimization, so I change this, and then I write this in the standard form. So so this is the x problem, this is the y problem. So let me, this x problem is a quadratic problem, by the way, because it's a circle, okay? So it's a quadratic problem. The optimality condition of this problem are the KKT conditions. So let me review quickly the KKT condition. This is the multiplier for dash. So we take the derivative with respect to x, is -1, and then this times alpha, it will be 2x alpha. Well, if you want alpha multiply by, is 2x alpha is over here, 2x alpha is over here, and this is 0. This is the gradient of the Lagrangian equals 0. And then we have this times the multiplier, the complementarity condition has to be 0. This is less than or equal 4, which is the actual condition. And then because the problem, original problem, this is less than 1, and this is a minimization, so this alpha has to be non-negative. Again, if you remember, these complementarity conditions are problematic in many sense, because we are just jumping this 0 or this 0, which means we are jumping from one axis to the other, so to speak, and this make trouble any kind of computational algorithm that you may want to implement. Okay, so this is the KKT condition for this problem. I do the KKT condition for the second problem, the same thing. Derivative of the Lagrangian with respect to y is -1, and then is this 2x, the y, sorry, is 2y beta, which is equal 0, then beta times the constraint 0, which is the quality of the complementarity condition, and then what we have over here is the inequality, and then for the same reason this multiply has to be non-negative. Okay, so this is the optimality condition of this problem. First order optimality condition, necessary, not sufficient, so we are moving in the necessary framework. So we may identify points that they are good, they are equilibrium at other points as well. So they are not sufficient condition, because if we try to solve sufficient conditions, we get something more complicated than the initial problem, and we don't want to do that. So we typically don't forget about sufficient conditions. Okay, so so anyway, one way to solve this problem is, well, we want a point in which the optimality condition for both problems together is satisfied, right? That's my only condition. So this is what I'm doing here. This is the KKT condition of the first problem, of the x problem. These are the KKT condition of the second problem over here. And I'm just minimizing one, because I don't want to minimize anything. What I want to just is to get a solution for this set of conditions, right? And then, well, I'm using here GAMS. I guess you should be familiar with some, either GAMS or ample or whatever other technique. I'm using a sophisticated solver, which is Kenitro, because again, dealing with this complementarity condition is complicated. So if you use a conventional nonlinear solver, that might not work properly. So I'm using this one, which was designed particularly to solve problem with this type of constraint. It doesn't mean that this is going to be solving this problem properly, but anyway, you should be careful. If you want to solve optimality condition of this type, you have to be careful with the solver that you use. They are not the same. Okay. That's what I'm saying here. So anyway, I'm saying that I want a significant number of decimals, and I specify the variables, the x and y, which are the variables of our problem. Z is just the objective function value. A and B are the alpha and beta, the two beta, the two multipliers, and then an important thing, I'm initializing everything. For this kind of problem, if you do not initialize everything, you may easily not get the solution of the problem. So this is why I'm insisting here. So initialization is important. In this case, I'm doing a trivial initialization, x, the initial value for x1, initial value for y2, initial value for alpha 3, initial value for beta 4, and that's it, so no problem. Anyway, this is just the description of the problem. As you know, you can do that in whatever solver you want. And I solve this using Canitro with this initial value, and I get this solution. If you can check, actually, that this solution is this point, okay? And we will see later on, okay? Yes?
But since it's generalized Nash, right? You may have more than one solution.
Yes. So anyway, when I'm solving this, I can start in the point a different starting point. I may get different solution. I may decide instead of minimizing one, which is a little bit a stupid thing to do, we will discuss this very carefully. We may use a particular interesting objective function here in case that we have many equilibrium to try to get the equilibrium which is interesting for us. From the point of view of this objective function, we will do that extensively later on. But for the time being, let's just, in this case, yeah. Well, yes, of course.
So for this type of problem, is it best to continue with non-linear constraints, like complementary constraints that we have, or rather it is advised to be linearized?
I think if you can linearize, do it. So, yeah. Yeah, in the case of a linear problem, if you can actually, instead of writing the KKT condition, writing something different over here, if this problem is linear, then we will have primal constraint, dual constraint, strong duality, equality. Generally, this is much better. So the idea is to try not to use KKT condition if you can. Is that?
Is better.
Yes. I mean, the KKT condition, if you can not use them, that's the best option. Okay? Because these things is problematic. So you have an alternative way to express that, which is not that one.
But also, like, second benefit is that we are getting rid of non-linearity.
Yes. Well, yeah. It depends on the problem that you are addressing. Sometimes if you write the primal constraint, the dual constraint, and a strong duality equality, you may get a linear problem. But depending on the problem, this might not be linear.
Yeah.
Depending on.
Like already convex or linear problem.
Mm-hmm. Yes. So anyway, and just in general here to describe, yeah. Okay, so that's the solution. Is this an equilibrium? Let's check that this is an equilibrium or not. Okay, for that, we already know that we have solved the optimality condition of both at the same time, but let's do interesting checking here, which is what I'm doing here is basically I'm fixing the y to the optimal value that I got in the equilibrium. So this is the y, 1.9364 whatever over here. So I'm fixing this value for the y and solving for the x. So this is the x problem. Okay? So if I do that, I actually get 0.49999, which is basically this 0.5 that we have over here. So we have verified that if we fix the y to the equilibrium value and solve the x problem, we get the same x that we had previously. Okay? We had to do that all the time. If you have a very complex, sophisticated problem and you solve the KKT condition, you solve this over here, you may get many things. You may get things point which are equilibrium, point which are not equilibrium. So it's pretty good idea when you have identified one particular point that this suspect to be an equilibrium is a very important thing to do something like that. Okay? So we fix to the value of the y problem and solve for this is just the x problem. We solve for the x problem, we get the same thing. So we are happy with that. And then the other way around, sorry, we fix the x value as the one exactly we got from the solution of the KKT condition through the auxiliary problem, and then we solve for the y, and we get this point over here, which is pretty much exactly the same than the other one. We call that, in a more sophisticated way, diagonalization. So we just fix the value of one problem, solve for the other, and if nothing changed, then we are in an equilibrium. Okay? We can eventually use this kind of thing to solve the problem, so why not let's assume a value for the x, and solve the y problem, get 1y, then fix the y, and solve the x problem, and keep doing that. If you do that, generally you get to nothing. At least this is my view. It's not generally a good idea to do these kind of things, unless you don't have any other option. I don't think this is a good idea. And if the problem is sufficiently complicated, probably it will work in this particular problem, but in general, there is no guarantee of convergence. There is no any guarantee for this kind of techniques, okay? And in that sense, I don't think they are very good idea, those techniques, okay? So actually, if you solve a problem to identify this point, which is what I'm doing here, so I'm maximizing the height, I'm maximizing actually y, which is the height, okay? Subject to being inside the two circles, you get this point, which is actually the same point with a slight variation because of the ring. So this point is actually the equilibrium, okay? So this is an equilibrium. Is the joint solution of two optimization problems, okay? Of many, 3, 4, 5, that's an equilibrium. I think it's pretty close to the real world, because most of the time that you make something or try to participate in a market or whatever, the neighbor or your competitor is affecting what you're doing and the other way around. So this framework, I think, is pretty appropriate for understanding this problem. We were discussing yesterday afternoon a number of problems. For instance, if you are in electrical system, a distribution system, and you want to organize mechanism in which every one of the agents is acting by itself, trying to do whatever. So most of the time we have problems of this type. Nobody will agree in a single objective function. There is no leader and many followers. There are many leaders. If you want to do a decentralized type of decision-making framework for people interacting in a market, you have many leaders. And people like to be leaders, not to be followers. So I think for this type of problem, the equilibrium is a natural way to express the problem. Okay? Equilibrium is, we will say a few things more later on, which is important. Well, but what we are going to do is I'm going to describe 3 types of models related with equilibrium. One is related with the, let's say we have an operator of the gas system and an operator of the electrical system, and they don't touch each other, so they are different entities that typically they do not communicate it. So it's very complicated to say, let's build a model which is a single model for both of them. So we have a new entity that actually run both systems, electrical and gas system, and get the optimal solution for both of them at the same time. This is kind of complicated to do. So can we do understanding a better way if they operate it independently and they communicate to some extent? Can we improve the type of solution? Can we get better solution, better understanding of what is going on? So this is what I'm going to do in the first thing. So is the equilibrium is between the problem of the gas ISO and the problem of the electrical ISO. Okay, there are 2 problems. They're interrelated. We cannot solve one without solving the other. We have to solve both of them at the same time. This is an equilibrium. Okay, so this is what we will do, and then we will say we will produce a more general type of market in which we have different, let's say, electricity producers, gas producers, consumer of electricity, consumer of gas, producer that produce gas and electricity at the same time, and electricity producers that produce electricity and buy gas, so consume gas, because they use the gas to produce electricity, okay? This is the kind of things that we will do. We will not do things like a gas producer and electricity consumer. So we will not cross over, we will not mix together consumption and production, unless is you have to buy gas to produce electricity, this particular case only. Otherwise, we are dealing with collusion and things which are at least illegal in the market. We may be willing to study illegal market, but it's not that useful in that case. So this is the kind of thing that we do. That will do that in the case this operational equilibrium. And then we will do investment equilibria. So can we extend this type of model to make decisions instead of building new plants? This is what we will do in these three type of models, okay? So an important thing, an equilibrium is not a decision-making tool, because for building an equilibrium model, you have to know everything. So if I have to solve the problem of the x and the y, I have to know all the constraint and all the data of the x, all the constraint and all the data of the y, and I have to solve both of them together. Okay, so I have to know everything. If you're a market participant that you're trying to sell gas or sell electricity, you don't know everything. So typically, if what you have to do is to produce effective bid to buy electricity, or effective offers to actually sell electricity, you don't use this type of models. This type of model, they are more like simulation tools that allow you to understand what is going on, and based on this understanding, you can do some things like, well, I understand that, so I know a better way to offer, or I know a better way to coordinate the two, let's say in the particular case, the ISO of the gas and the ISO of the electricity. This is the kind of thing that we do. So an equilibrium is not typically a decision-making tool, because basically they give you a global picture with the information of everything. If you want just to offer in the market, for instance, you don't know everything. You know your own stuff, not everybody else's stuff. Okay. So this is important to have in mind for the analysis that we are going to do later. Okay. Okay, so let's go to the problem. Well, this work is pretty much related to the work of Sheng. Well, he's now has already graduated, and my colleague, Professor Rantincios Hansi. So anyway, I will do a very nice example. I hope you agree that this is a very nice example. And then we will provide you with some additional background for this type of models, and then we will formulate the model and trying to solve the model, and I will have a case study and some conclusions. So this is a more traditional type of presentation that I guess you are familiar with that, but let's go a very simple model. So let's say that we have a gas ISO, which is operating two gas plant. Is this G1 and G2, still very simple things. So this gas ISO, the first one is very cheap. Is 1, the cost of producing gas with the gas source 1 is 1. The cost of producing gas with the gas source 2 is 3. So I'm going to use that as much as I can. I don't want to use that because it's much more expensive. I have to supply a gas demand of 12 plus some gas for electricity production, which pop up here like this blue stuff, which is somehow exogenous to this problem. So my decision is G1 and G2. I'm the gas operator. I want to operate, to schedule, or you want to dispatch the gas system for G1 and G2 in such a way that I supply this 12, which is my gas demand, in a very simple way, and the additional gas that I need to transfer to the electrical guys to produce electricity, right? Okay, this is a balance constraint. Right? So this is the price of gas. It's the marginal price of gas, as you typically know, because this is a balance constraint. And then I have a bound. So my gas source number 1 is bound by 10, not more than 10, 0 to 10, and is bound by 14, 0 to 14. And the gas production, of course, has to be non-negative. Very simple problem. But a problem which is connected over here with the electrical problem. So in that sense, something not that nice in that sense, okay? So the power ISO. So the ISO of the power system, let's say that is buying gas to produce electricity. So I'm using the price of the gas, which is lambda G. This is going to be the price in which this electrical ISO is buying electricity. That might not be the case. Is that what happened in reality or not? So, you know, this gas ISO is producing prices instantaneously, which are transferred instantaneously to the electrical system to dispatch the electrical system. Okay, just let me anticipate that we have some kind of aggregation in this price. So maybe typically gas prices are daily. We have a single price for the whole day. Electrical prices are hourly. So there is something over here different than what I'm doing, okay? But, okay, so let's go to the power again. So this is the quantity, the price of the gas, and GE is the quantity of gas I'm bringing from the gas ISO, right? And I want to minimize, then I have a power plant which is not gas-based. Let's say that this coal or whatever, and the cost is 2. Over here. So to produce a quantity of electricity P, the cost is 2. And then I have the balance constraint for electricity, which is I'm assuming that the conversion gas to electricity is 1/2. So I have 1/2 of the gas is giving me electricity, and then P is the actual electricity that I'm producing with the alternative machine, right? And then has to supply the demand for electricity, which is 14. Okay, and this is the balance condition. So lambda E, this is the electricity price, right, in the marginal sense. And my machine P is bounded by 10. So we have a limit of 10 over here. Very simple thing, 2 optimization problem. This is the problem of the gas ISO. It's connected to the electrical ISO because it's selling gas to the electrical ISO to produce electricity. This is the electrical ISO, which is connected to the gas ISO because it's buying actually gas from the gas ISO and at the price established from the gas ISO as well, right? Okay, so let's just emphasize a little bit more that. So this problem is the gas clearing, market clearing for the gas. Not very different than the actual complicated gas clearing that we have. It doesn't matter if we have two, in this case, 2 gas sources, or we have a few hundred or a few thousand, it doesn't matter. The problem looks like pretty much the same thing. This is, of course, multi-period. So we need a multi-period stuff here, and all constraint linking the time period, whatever we need. But at the end of the day, not very different than that. Okay? And the electrical system is pretty much like that as well. So this is the power clearing. And again, the same thing. We may have multi-period, many machines, some of them gas-related, some of them not gas-related. Maybe we have even uncertainty, complicated uncertainty related with renewables, and so on. But at the end of the day, we have a linear programming problem with some connection with the gas problem over here. And the basic connection is that this electrical ISO needs gas, so it's going to ask for gas from the gas problem. And this gas problem is going to send the price. Well, you want to buy gas, then you pay this price. This is what we are doing over here.
So basically, Stekelberg game. Gas producer is
but they are at the same level. So they are not, there is no hierarchy here. Okay, so they are on the same level. So yeah, we will get the Stekelberg games later on, but not now. Okay. So that's the problem. So I should perhaps draw this at the same level, not up and down, but at the same level. That will be better. Yes, yes. There is no hierarchy here, so we can start from the other. Okay, so what I'm doing, well, let's solve this problem cleverly, because all of you are clever, I know about that. So let's solve this problem just looking at the problem, right? Because, and then we will see we can solve it in a more complicated way. So let's look at the gas problem. So the cheapest one is G1, okay? So I want to use G1 as much as I can. G1 is upper bounded to 10, so G1 is going to be 10 at the maximum. Okay, and then what we need, the rest of the gas, which is 2, this 12 minus 10 is 2 plus GE. 2 plus GE has to be covered by G2. Okay, so since this is going to be covered by G2, we assume that the problem is feasible, so we have enough gas to actually supply everything that we need. Then I have the marginal cost is going to be 3. Of gas, right? Because, I mean, whatever extra that we need to produce is going to be with this machine, that the cost of this machine is 3, so lambda G is going to be 3. Okay? And then let's move to the electrical problem. We can see that since just the lambda G is 3, and we need twice the gas that we need to produce electricity. So it's clear from here that since the price of gas is 3 and just producing electricity with the other power unit is cheaper even that without the 1/2. So we are going to use this P as much as we can. So for meeting the electrical demand over here, P is going to be at the maximum. So the maximum is 10. So P, which is the cheapest, go to 10, which is the maximum over here. And then since this is 10, okay, then 1/2 of GE is 4, right, which is left out of this 10. And then GE, 1/2 of GE is 4, so GE is 8. And then since we already know GE and 10 was covered here by this G1, so G2 is going to be 2 plus GE, 2 plus GE, which is 10, right? Okay? And then slightly a little bit more simple as well, but so anyway, if I want to calculate now this lambda E, which is the change in the objective function, when I change a little bit this 14 to 1. So if I change 14 to 1 to 15, the increment is 1, but I need, because of this 1 of GE, we need double of GE. To get 1, I need 2 of GE, right? So the increment instead of GE is going to be 2, means that changes of 2 in GE over here that we need, that produce that lambda E is actually twice lambda G. So lambda E, the electrical price, is actually 6 in this case. Okay? Everybody. So we have solved the problem, this equilibrium problem, because it's very simple. So let's solve it in a more formal way, because and see if we get the same thing. So anyway, this is the gas problem. So I'm now using, as you mentioned, the primal constraint, dual constraint, and strong duality equality, which we have over here. So this is the primal problem. This is the dual problem. Just quickly, 12 plus GE over here, 10 over here, 14 over here, and then 1 and 3 is 1 and 3 over here, and then being careful with the signs, we have this mu1 and mu2 has to be non-positive in both cases. And the strong duality theorem is telling me that the subjective function of the primal problem and the objective function of the dual problem has to be the same at the same time. We can see that this is nonlinear because GE is a variable, lambda G is a variable as well, so we have bilinear terms here that may make life a little bit more complicated, but anyway. This is the optimality condition of the gas system. We do the same, we write them here. So this is the primal, this is the dual, this is strong duality equality. So the optimality condition are these, okay? So this is the primal constraint, is the primal constraint of the primal problem, the dual constraint of the dual problem, then the strong duality equality, this objective function is equal to this objective function, and then these two constraints I have over here, put it here to make everything complete. So this is the equivalent to the KKT condition of the gas problem. Okay, the first order optimality condition of the gas problem. Okay. Everything happy? Everybody happy with this?
Just should I mention that lambda g is free variable here?
GE, no, but I'm gonna, G is a constant for me.
No, lambda g.
Lambda G, yeah, I'm not saying anything about lambda G, so it's free. Okay, we may say explicitly that this is free, but it's free, yeah. Since I'm not saying that this, okay, perfect, yeah. Perfect, yes, lambda G should be free. Okay, the power problem, or the electricity problem, if you wish. This is the primal problem, dual problem, quickly, lambda G and 2, lambda G and 2, and then 14 and 10, 14 and 10. So this is the primal constraint, this is the dual constraint, and the strong duality equality, the objective function of this equal to the objective function of this, okay? So I do the same, I write the primal constraints over here, the dual constraint over here, the strong duality equality over here, then GE non-negative, P non-negative, and the lambda, both of them are free. Because I'm not saying that, not saying anything, so they are free. Okay, so they are the optimality condition of the two problems. So we want to solve both of them together, okay? Because if we solve both of them together, we get the equilibrium, the solution of the two problems at the same time. And this is what we do. So we produce and we minimize one, as we did previously, and this is all the constraint as we have write it down. So the primal constraint, dual constraint, and strong duality of the gas problem, primal constraint, dual constraint, and strong duality of the electricity problem. They're all of them together over there. So, okay. And I have nonlinear stuff here, like this one. Of course, we can do many tricks to get rid of these nonlinearities. There is a lot of technique to look into that, but we will not look at that at this point. So I solved this problem. This is the GANS version of the problem, a very trivial, straightforward GANS version of the problem. And if we solve the problem, we get happily exactly the same solution. So I'm using, again, not using Canitro here. So, well, this is not that problematic because we don't have complementarity condition here. So I'm not bothering here to specify to use Canitro or any kind of solver particularly oriented to this type of problem. So, and you can see the solution in this problem. I'm not initializing anything. No, I'm not initializing anything. That means that this problem is solved very easily. So,
which solver is used here?
I don't know. I don't know. But Canitro should work well. But anyone should be work well, yeah. A non-linear programming one, yeah.
Sorry, Antonio. Why don't you use a system of equations without auxiliary objective function?
Yes. No problem.
Is there any preference?
No. Because at the end of the day, well, the only thing you can say, this is, well, I didn't want to go into NCP, so, okay, let me go back. So if you have, this is the system of equation that we have to solve, this one plus this one. We have a mechanism to solve that efficiently without an auxiliary optimization problem. Why not doing that? But sometimes in the case, if those are KKT conditions, as in the previous problem, then they mathematically we call what they form this collection of KKT conditions together as a mixed complementarity problem, and we can use a particular solver that solves these mixed complementarity problems. Those solvers, my personal experience, I don't want to say anything, but personal experience that they do not scale very well. So sooner or later, you may get trouble with the scaling of those problems. So you may want to solve solvers which are more, in this case, I'm just using a optimization solver, right? But yes, you can, if you have a mechanism to try to solve this system of equalities and inequalities in an effective way, that is a way. One way to do that is using a solver which solves mixed complementarity problems. Okay, yeah. Okay. Have been. Let's see, we are going to do something interesting here, which is sometimes an equilibrium is equivalent to a single optimization problem. Those equilibriums are not very interesting. This is one of those not very interesting equilibrium, but we will going to change the equilibrium quickly to get things more interesting. Okay, so let's solve the problem, the gas power problem together. So I have combined the gas ISO and the electricity ISO. I have combined them to work together, to merge and to produce a single entity that ran the two systems. So this is the problem of the joint entity running both the gas system and the electrical system. So we want to minimize the gas that we use, just the gas that we use in general, not the gas that we use for gas consumption and gas electricity, because they are merged together. So we have to minimize all the gas that we use. It doesn't matter for what is using this gas. So minimize the quantity used by the first gas source plus the gas produced by the second gas source, and then plus the cost associated to running the electrical machine, which is not gas-based, okay? And then we have the gas constraint and the electricity constraints, okay? So the gas constraint is telling me that G1 plus G2, which is the production of the gas, is equal to 12 plus the gas that we use for electricity, which is an internal variable in this case, okay? And this is the price of gas. And then this gas source 1 is limited, it's bounded by 10, this is bounded by 14, and here we have the balance of electricity, the same thing. This gas over here, we use the conversion factor to transfer to electricity, so this amount of electricity plus the electricity that we produce directly is going to be 14, which is the demand for electricity, and then this P is bounded by 10. Okay, so this is the same thing. This is the problem of the two entities together, if we are able to combine them to get together. So this is the solution of this problem. Again, this is a linear problem. So this is much nicer than previously, and the solution is the same. Okay? So why solving a complex equilibrium problem if we can solve a simple optimization problem? Okay? So if we built an equilibrium problem that is equivalent at this case to a single optimization problem like this one, we should never use the equilibrium approach, because the equilibrium approach is much more complicated. It leads us to equations which are complicated to solve, concepts which are not that easy, like the optimality condition and so on. So we should have a very good reason, and the good reason that we need is that we don't have this equivalent optimization problem. Okay, and we will see, and I say here, we'll see, okay? So let's move a little bit on. So anyway, in many places, this is a blessed country because wind all over the place, plus a huge battery in Norway that can probably, the Norwegian hydro battery probably can store, I don't know, probably several years of the actual consumption of the whole Denmark. I don't know the details, but the lake in northern Quebec can actually store 3 years of the whole consumption of the entire Canada. Canada is a tiny country in terms of population. It's a big country in terms of space, but it's smaller than Italy, for instance. I think Canada should be, I don't know, in terms of population, it's a small country, less than 40. Okay.
Your microphone.
Oh, sorry, yes. Thank you. So anyway, the lake in Quebec can actually store several times the consumption of the whole Canada for several years. I guess this is the case of the lake, of the reservoirs in Norway with respect to consumption in Denmark. So anyway, this is a really special situation. But in some other places in which things are not so nice, for instance, the case of Spain, basically, the system of Spain is interesting because it's gas and wind with a base load of nuclear. Exactly the same thing that in Texas. Actually, the actual installed capacity is about the same, and it's the same thing. Wind, a little bit less wind in Texas in proportion, and then gas, and then a baseline of nuclear. So I think I think this is an interesting combination because we integrate more and more renewable. We need some kind of flexibility in the system. If we don't have a huge batteries will be the best. So, but if this huge battery is not around, gas is an interesting alternative. Gas is not very terrible from the environmental point of view. So I foresee that in many places, certainly in the US, the growth of the substitution of gas by of the old coal plant by gas unit is happening very rapidly, particularly, for instance, the state of Ohio. When I arrived there at the beginning of 2014, it was basically 90-something coal. Now it's below around 70% coal, and the rest, almost 30%, is basically gas. So the gas is, that has been just 6 years. So gas is rapidly substituting coal for many reasons in many places because of environmental reasons and in some places, but mostly because of economical reasons. So nowadays, to run and operate combined cycle gas turbine is, from the economical point of view, more attractive than using some other technology. So that's an interesting combination. So those are, sometimes it's very interesting to get a look of what is going on in the US. The Energy Information Administration, they produce a lot of interesting data related to energy for the country, and the European Union produce a similar type of information, and the International Energy Agency produce information similar to that as well. So it's interesting to look at that, and everywhere you look, you can see that there is a significant growth of natural gas. So over here we have a projection 2050, and we can see that basically there is a major increase on gas. So system like renewable gas and maybe something else because of historical reason seems to be a very situation that happen in many places. What is happening right now, I mentioned in Spain and Texas. So anyway, the model that we are going to build, so this is a good reason, again, to look carefully to the interaction between gas and wind. Okay, gas and renewable, or electricity and gas, because if we are getting more and more gas into the system in such a way that the system becomes something like in Spain. So if I remember right, it's about 25% is wind, the rest is gas, and there is some nuclear and minor coal around. And so anyway, in that case, the price of electricity is actually absolutely linked to the price of gas. So the two systems are heavily linked in all respect. Operationally, we move the gas to accommodate renewable. So from the operational point of view, they are linked. We use more gas as the renewables do not produce for whatever reason. The marginal price is going to be almost systematically the marginal price of gas. So the two systems are heavily interrelated, and which is more important. And we integrate more and more combined cycle gas turbine. The gas infrastructure may become very stressed. Okay, so if we do not improve the gas infrastructure, building a gas pipeline is a complicated thing everywhere. Building a transmission line is impossible. Building a pipeline is impossible. In Europe, I think both things are basically impossible. If you go to some special places of Europe. It's very difficult to build new infrastructure. So we stress, because you use more and more gas for electricity, we are stressing the gas infrastructure. This gas infrastructure may produce bottleneck, trouble in the operation of the system. So it makes a lot of sense, like Pascal say, that you have to actually represent, internalize in the unit commitment, if unit commitment is not used here in Europe, but in the case of the US, in the unit commitment, we had to internalize the effect. We had to make the unit commitment aware of the network interconnection of the gas system. So anyway, that's what we are going to do over here. So anyway, the systems are heavily interconnected because of many reasons. So we should be able to look into that carefully, okay? So anyway, in this particular exercise that I'm gonna do right now, because of the strong interconnection, I'm gonna basically analyze in this model the effect of different type of information interchange, of coordination between the two of them. In the example that we have previously, remember that what I said is the actual price of the gas system is transferred directly to the electrical system to operate the electrical system. We do that in reality? No. And we will see what it is. Okay, that's a little bit, well, let me say that what I'm saying here, diagonalization is the technique in which we have two problems interrelated, solving one, fix the solution of this one, and then solve the other, fix the solution of the other and fill the first one, and keep iterating. This is the diagonalization. And my experience, I think some people have another experience, I think Gerald's experience as well, is that this very rarely work in an effective way in many problems. So my observation will be try to avoid that unless you cannot. Sometimes you build some complicated problem that this is the only option to do. Anyway, this is the gas model for me. I'm not going to go into detail of the gas model. This gas model maybe are relaxed. Maybe, their gas model are more complicated than electrical model. What we tend to produce is description of the non-linearities using second order conics approximation. You can do that nicely for gas system, and you can refine the relaxation using other type of envelope, like McCormick envelope on top of the second order conic relaxation. You do that, and whatever you get something like that, a little bit messy. That I'm not going to look into that, but this look like that. So the particular type of implementation that we have been doing in this particular application is that we have a model look like that. So the R and S are the variable related with the gas model. I guess the R are the sources, and S is an intermediate. Well, actually, S are the conic constraint, are the variable related with the conic formulation. By these, I mean the conic part of the linear, because this is just linear. And we have over here Y. This Y over here is the one interconnected with the electrical model. So this is the gas that we use for producing electricity, and it's going to interconnect with the gas model. And this is the quality constraint, so this is going to be the price that we have to transfer to the electrical model. Okay? This is the structure of the problem that looks like a little bit like that, more complicated. So this is the gas model. Those are the KKT conditions for the gas model. In this case, that's the KKT condition. In the case of, we may not use, sorry, let me go back. In the case of gas model, if this is a second order conic, we can actually write the dual as well and impose primal constraint, dual constraint, and strong duality equality in this case as well. Yeah.
Just one question. Because second order conic problems, they are convex.
Yes.
And why we need McCormick relaxation? Where we need this relaxation?
No, it's transfer for transfer when this is a nonlinear problem, a nasty kind of nonlinear problem. And when we relax the problem, the original nonlinear formulation, which is not second order conic, and we produce a second order conic relaxation, then this relaxation might not work well. it depends on the problem, the application, but it might not work well. And I know that somebody is working on that. This is why I mentioned that. So,
I thought like you were trying to have this McCormick relaxation on the Conic.
No. If it's Conic, we are happy. We don't do nothing. Right. It's already convex. Yeah.
I just use McCormick to tighten
Yes.
and to see it effective. And your experience?
My experience, not for this equilibrium problem, but just for a joint problem in which we solve jointly a unit commitment with all the description of the gas system, is that what we did was convexify and see which is, and look at the infeasibilities, because the objective function is not that relevant. The relevant is the feasibility we want to implement it. And with just the relaxation, you get significant infeasibilities. Then you built McCormick envelopes, and because they are local, so you had to use a solution to build the McCormick envelope. So you build the McCormick envelope and solve the problem again with this McCormick envelope. You get a solution which is better, but still with some infeasibility.
Much better?
Significant better, but what this gets much better if you refine in a second time the McCormick envelope, because they are local, so you solve with the relaxation, you get a solution, you build McCormick envelope, you solve again, you get another solution, then you build new McCormick envelope and solve it again, and doing that, my experience with the cases that we have studied is that we get very tiny infeasibilities, That is what we did. What Chen did, actually. So anyway, that's the problem. So, okay, this is the gas model. This is the KKT of the gas model. This is the power model that you know very well. So I'm using here a standard linear programming. So the problem looks like that. If you do the full formulation, at the end of the day, you can collect all the information in terms of this X and Y. And the Y, the X will be the power production by itself of the system, and the Y are actually the gas that we have over here, the gas that we use to produce electricity. So this is the Y that we have over here. And this we are buying gas related with this Y, and this is the cost of gas in this particular case. So I make a difference between this U and this chi over here to be able to say, well, they are equal or they are not equal. In the previous simple example, I said they are equal, but let's see what happens if they are not equal, okay? So this problem is linear. Again, we may describe here the electricity market clearing using, again, a convex relaxation, a second order convex relaxation. Why not? We didn't do because, well, but I think it will be a good idea to do that as well. So, and this is the KKT condition that we have in this particular case. So again, conceptually, we have already described very thoroughly with the simple examples, but we have solving the gas price, we get the actual gas price. We use this gas price to operate the power system, and the power system needs quantity of gas to operate the system. Again, let's see if this is like the case of Texas of Spain, is a very significant part of the total production of electricity. Let's say if 50% is gas of the production of the system, they are fully linked. So to operate two independent systems, make less and less and less systems. So, okay. Okay, so one way to solve this problem is just what we did. Again, I'm using here KKTs, but we can substitute that with better things if we can. So I'm just being generic, but we want to minimize nothing. Since they are KKTs, we can try to solve just the mixed complementarity problem using a solver for that. And if the solver is good enough to actually solve the problem. And then, so this is the KKT condition of both the gas and the power system. And then we have the price condition. We have to establish which kind of price we want between the two of them, okay? And this problem may be complicated. Okay, we may have non-linearity, we may have complementarity condition, which are particularly nasty to deal in an optimization problem. We may have all kind of trouble here. I say it here, and we can try to fix that through linearization, convexification, whatever technique that we think which is reasonable within the framework of the solution of the problem. And of course, this is one of the critical points. If we can linearize that in a reasonable way without deviating or without simplifying the problem, then probably we can really solve huge problems. If we cannot do that, well, things will be a little bit more complicated. Okay, so this is the two problems in this particular case, and remember that this the chi that we have over here. If we say that this variable u, which is the dual variable of the gas problem, is actually the chi, which is the price to buy gas from the electrical point of view. If they are identical, it's exactly the same thing that the tiny example that we started with. It's exactly the same thing. So then we have an equivalent problem 6 for this. So we don't want to do that. But in reality, it does not happen. Typically, either the gas system, let's say, simplify the price, either do a temporal average. It's say the price for gas the whole day is a single price, so it's averaging actually the price of gas with respect to the operation. If we do an hourly operation, maybe also some spatial aggregation of the spatial averaging of the actual price. So it may all these kind of things, and we actually did study that. So we will, if we have a temporal average of the price of gas to be transferred to the electrical system, we have a spatial average of the price of gas to be transferred to the, and we have a combined average, then we cannot solve the problem together. Okay? Again, let me, we don't want this to actually operate one or two of the system, because we cannot do that. I mean, either we have a single entity and then there is no equilibrium anymore because we solved the problem by a single entity. We want to get inside what is important in terms of understanding the relationship between one ISO and the other ISO. This is the important thing, because for solving this problem, we need the whole thing. I need information of all the details of the gas system, all the details of the electrical system. I can do that in the study mode to simulate what is on. I don't want to know everything together to operate the system, because if I know that, I can operate the system jointly. We have automatically created this single entity which is responsible for the whole thing. Okay? But it's interesting, I believe it's very interesting to understand if there is no full price communication between one or the other system, which are the consequences. And if the consequences are very bad, we can go to the two system operators and tell you have to communicate better. If you do not communicate better, social welfare is going down in a dramatic way. So that's the point, that's the use of this type of models. Okay. Okay, and from the math point of view, they are fun. So if you don't care about gas or electricity, but care about math, I think those problems are challenging from the math point of view as well. Yeah. Okay. So okay. So anyway, we'll do the averages that we do. This is the price. Okay. Remember that this chi is the price that we use for the electrical system. So we can do a temporal, this is, forget about the notation, but this we are just, all the time period, the 24 hours of the day, we collapse in a single one doing the average. Okay? Since we have full different price in different location, because we assume that the network might be congested, we average in terms of locations as well. And for doing that, we actually weight every price by the demand in this node, which is what we call the load weighted average. And in this case, is the combined average in this case. Okay, so let's do, then before presenting the thing, be careful that we said we should not double count the gas that we use. If we count the gas that we use in the gas system, we should not count this gas again in the electrical system, okay, to compute the total cost. So because the gas cost appears in both problems, okay? So not double counting, is that what we say here? This is the cost of operating the power system without gas, and this is the cost of operating the gas system, including all the gas, and this is the total cost, whatever. So we have a number of studies which are based on a Belgian model of the system. Why to study Belgium? Maybe from Denmark, since Denmark and Belgium are small, nice countries, so that might be a good reason for doing that. But, well, why we did that? Well, maybe you should be aware of Professor Yves Smeers from Louvain, that he did a lot of interesting gas studies a long time ago. So when we look around for gas data, now we have a significant access to interesting gas data, which is available. If you're interested, you are welcome to let me know. But when we start looking at that, we couldn't find really good data for gas. We like to use case based on Texas because the Texas data and information of the system is fully available. And for instance, all the data in terms of the transmission, generation, wind production is pretty open in Texas, but we couldn't get information about gas in Texas in a clear, easy way. So we ended up using models of gas that they were available through many publications and interesting report of Professor Smeers. And that's the reason we're using that. And we connected using there has been a number of European projects actually describing the whole European network. So we use data from one of the specific data for Belgium of one of the ENSOE type of description of the system. And we connected them with the help of Anthony. And hopefully, probably it's just a simplification, but I think it's realistic enough to understand what is going on in this particular system. So this system is interesting in terms of gas-fired unit because about 30% of the system is gas. I don't know if this is very up to date, but at the time that we studied that, this is a small system. The installed capacity is about 14 nuclear power plant, so a small system, but 30% of this is gas, and this is the electrical system, this is the gas system, and this is what we study in a very exact way. We'll try to reproduce in a much more precise way that we could the condition of the system, because I believe, at the beginning to play with a small system is a good idea, but at the end of the day, if you want to understand what is going on, I think it's important to do something which is realistic. Something maybe realistic and small, which is this case, and that's good. It might be realistic and big if you can, or if you have the computational machinery to look at that, but we did our best to produce this to be as more realistic as possible. And this is my advice as well. So use tiny examples as long as you need to understand, to comprehend, to really catch all the details of the system, and then either big or small, but try to do something realistic, because otherwise that's the only way that you get really interesting input. I think IEEE network, well, they're nice, they're easy, but typically they are not realistic. So it's, if you can use networks which are connected to reality, I think using a careful description of the Dennis system probably is not that huge, and it's probably an interesting alternative to many studies. And okay, so that's observation as well. So. So I think we can go on for a while and then we finish. So anyway, that's the system that we use. This is the electrical demand in a particular day. I don't remember which day. But the demand, the peak demand in terms of electricity is about 12.5 gigawatt. And then the gas demand is something like that. This is the demand, a typical day. We just use 24 hours. We repeated the study for many days, and we are reporting here just one day. Probably we pick up this day because it's interesting the kind of effect that we observe in that one, okay? And basically, this is the result that we got. So basically, we are comparing here the perfect information interchange means that at every hour the electrical system is using the gas price produced for the same hour of the gas system. Okay, this is what we do in this case, and this is in this case is the total operating cost of the system that we have over here. This is the cost of operating the gas system. This is the cost of operating the power system. And over here, we do temporal averaging. So there is a single price for gas for the whole day. This is what we got, a significant increase in the total cost. This is the percentage value, so it's about 0.5%. This is the value of the perfect pricing. So we don't have perfect pricing, but we have an averaging pricing. We are losing 0.5% with respect to the total operating cost of the two systems together. This is a lot. It's a lot of money. 0.5% is a lot out of this amount that we have over here, of those millions. Okay? So a small percentage of improvement is a major improvement, and the other way around. If you deteriorate the solution in a small percentage, this deterioration may be very dramatic in terms of absolute values. Okay, we see that we have a similar effect if we do a spatial average of the price. So the price is the same all over the region. It doesn't matter if the pipeline are congested or whatever. We just average everything, and this is what you get in your home. You don't pay different prices, I guess. Wherever you are in Denmark, you pay the same price for electricity. I guess this is not a good idea, because in some places, well, it's not from the economical point of view, it's not a good idea, because in some places it may be very complicated to get the actual electricity over there, so why subsidize those guys that decide to live over there? They want to live over there, then they should pay whatever it costs the electricity to keep it there, right? So anyway, that's the basic argument. Of course, we can say every citizen should have the same right and the same price, but anyway, there's an interesting thing. And the combined effect, is not as dramatic at twice the effect of both of them. So it's a little bit higher, but not much. So the combined effect is not the summation of the independent effect of both of them. And if we look at that, we can analyze this in detail, but this is the kind of distortion that we can see. This is the gas price in this particular case, and we see that the perfect price is the blue one. So we get significant changes in the price. So the price changes in significant ways. We can describe or dig into detail what is happening in this particular case because it's low, and in this particular case because it's higher, but I don't think this is much relevant for this time, but this is the kind of happening. This is the power prices that, again, we have a very significant change with respect to the perfect one, which is over here. This is for every hour the load-weighted average of electrical LMP. And you can see significant changes. In this case, we can go from 60 to almost 85. So there is a lot of significant changes. Well, there's some observation and explanation over there. Okay, so let's go to just conclude this analysis. So most wholesale natural gas system employ prices that they're basically similar. They're akin to combined averaging. So the price for gas, it does not depend on where you are. It does not depend on the hour of the day. It's a single price for the day. This has a significant impact. In the case of the Belgian system, this is the impact, which is a very significant impact in terms of cost. So this is something that we can go to the operator and tell them, hey, gee, look at that. You may want to look at that because we can save significant money out of that. Okay, so so those prices basically introduce efficiency losses in terms of the cost of the system. They are mixed impact, so it's not the same to the type of averaging that you will do. And I think this is, we may try to combine the operator to look into that, because we can reproduce that systematically in different studies, in different analyses. Might be a good incentive for trying to coordinate it or to change the pricing practice to some extent, right? And well, we have this in a paper, which is, if you're interested, I will be happy to send you this paper. It's still under review, and it's, I think, in my colleagues, Rantinsius Hansi, have available this paper, all the papers under review in his webpage. Okay, so I think that's it. I don't know if you have any question about this particular, the introduction of the equilibrium and then the use of the equilibrium to understand the interaction of these two ISOs, not with the purpose of providing a tool for one of the ISO to operate the system, but to understand what is going on, which are the consequences of the interaction of one ISO with respect to the other. That was the purpose. No question. Okay. Okay, so then we can 10 minutes or so, and then we will continue. Thank you.
Thank you.
Yeah. Okay, so what I'm going to do now is to describe a situation which is different. So I'm not going to look now for the operators, but just to independent producers. So again, this work is related with the PhD work of Shen Chen and my colleague Rantinsius Hansi. So what I'm going to do now is to look at the problem of gas and electricity, just looking at the agents. I don't want any longer to look at the ISO. So let's see what happens if within what we have an ISO actually clearing the market, but now the emphasis is going to be to the actual behavior of every producer, every consumer in that market. Okay? So we are going to do a very simple example to understand what is going on, and then we will do a more general analysis of the problem. Okay? So very simple equilibrium in this case. I'm using a Cournot type of analysis here. Let's say that we have a gas producer number one. So this gas producer number one is producing some gas for the actual supply of the gas demand, and this is the gas for electricity demand. And then we have a price of gas. And I'm going to assume that the price of gas, just for the simplicity in this example, that is not a dual variable, which makes things a little bit more complicated, but this follows a Cournot type of rule. So this is a constant, so we have an intercept and a slope, and this price of the gas depends on all the gas. The gas that this producer is producing for gas consumption, for electricity production, and then it depends not only on the action of this gas producer 1, but also of gas producer 2. Okay? So the price depends on the action of myself and my competitor, because I'm considering only two gas producers, 1 and 2. Okay? Both together alter the price. This is the price. And I want to maximize my profit, which is the price of gas, this price over here, times the quantity of gas that I actually sell. It doesn't matter if I sell this quantity for producing gas or producing electricity, minus the cost of producing gas, multiplied by the quantity of gas that I'm producing. Okay? And then I have a capacity of gas production, so the gas that I produce for gas and the gas that I produce for electricity is upper bounded by the maximum capacity of production of the gas. Okay? Very simple thing. I have a very simple price structure because I want to understand how this works in principle. Then I will do a more general thing. Okay? This is the same thing for gas producer number 2. Everything is identical, but 2 instead of 1. So this gas producer number 2 get the same price because the price is unique for the market. This is the rule for the price, which is equivalent to the market clearing. So this is equivalent to a problem of market clearing as the one that we have described. And this depends on the production of the previous gas producer 1 and the gas production of this one, the second one. Okay, and the profit is the revenue, which is the price times the gas production minus the cost, which is the gas production times the actual per unit cost, and is upper bounded, this one. Okay, so they are both interacting, and this is the price equation, and then try to produce gas in such a way. Of course, if they produce a lot, the price goes down. So they want to produce, yeah. Because I have it here. So it's a variable of the problem. Let's say we can call G1 and G2, G and E, like the decision variables, what the producer decide. But this is also a variable of the problem because it's there. So it's like the flow in a power flow. So if you are trying to, let's say, establish which is the power output of every unit, the power flow, the flows in the lines, they are variables if you define them, and they are there in the problem. They are variables of the problem. So we should call these variables should be inside the problem as well. They are optimization variables. They are part of the problem. They are not the variable that you move to get what you want, but they are variables of the problem. You may just take this and put it over there and get rid of this variable. But if you explicitly describe this variable, then it's a variable of the problem. Okay? I can get this over here and put it over there, and then the only variables would be G1 and G2E. But if I define this variable with this equation, then it's a variable of the problem. In the same way that you're solving an OPF problem, the production, the P and the Q of every generator are control variables that control every generator, but the flow in the lines, they are variables of the problem. And you have to define them like optimization variables, even though you don't have control over the flows. So it's the same thing. Perhaps a little bit more confusing here, but for solving this problem, this is a variable you have to take derivative with respect to the variables as well. Otherwise, you don't get the solution. Anyway, interesting observation. So this is the power problem that we are going to connect to the gas problem. So the connection over here is that some of the this gas produced by the producer, gas producer 2 in this case, go for producing electricity, and this G1E produced by gas producer 1 is going to produce electricity. So I'm going to use them to produce electricity. So this is the power producer 1. And we will see here. So we have, this is the, again, I'm a power producer. I sell power. I make money selling power. I want to maximize my profit. Okay? So my maximum profit is the revenue, which is the price of electricity. Again, I use a Cournot type of simple example to describe the price. So this is the price of electricity. For the same reason, it's a variable in this problem. Time the total quantity of electricity that I'm actually producing. And the total quantity of electricity that I'm producing, it depends on two things. The electricity that they produce using gas, which in this case is the price of gas times the quantity of gas that I have to produce. I'm producer 1 and using Q1G is the quantity of gas that I'm buying from the gas market, and in this case are the two gas producers together. Okay? And this is the quantity of electricity that I produce just using units which are not related to gas unit. Okay? So my total electricity is rho 1, which is the conversion factor from gas to electricity, times the quantity of gas that I'm extracting from the gas market, plus the electricity that I produce directly using machines that do not depend on gas. Okay. But the price depends on the total electricity. So this is the electricity that I'm producing, E1, and E2 is going to be the electricity produced by the second producer, and this is the price of electricity following a Cournot law over here. And I say, well, I have a bound of the total gas that I can buy to produce electricity. I have a bound of the total electricity that I can produce using the machine different than the gas. And then I have this decoupling condition, and I say the gas that actually I'm extracting from the gas market plus the gas that my competitor power producers extracting from the gas market has to be equal to the gas that we together get from the gas market, which is this 2G1 and G2. This was it go to the gas producer. This was G1, G2, or if you want, this G1E is the gas for electricity, G12 is the gas for electricity. Both together is the total gas that we have out of the gas market, and this should be equal to the gas that we buy to produce electricity in the electricity market. This is consistency constraint that we will see later on. Okay? So this is the electricity producer 2, is the same thing. So this is the price for electricity times the total electricity is the revenue minus the cost, has two components. First one related with the gas that we produce, that we buy to produce electricity with the price of gas over here. PG is not a variable of this problem, it's PE, pi E, sorry, because pi E I'm defining here, but the price of gas depends on the other problem. Okay? And this is the cost of electricity, producing electricity by itself. The total electricity is what I produce out of gas plus what I produce directly, priced that way, depending on my electricity level and the electricity level of, and the electricity level of the previous producers. And then I have upper bounded the gas that I can use, upper bounded the electricity that I can use, and then this is the consistency constraint, the gas that we use in electricity over here has to be equal to the gas that we get out of the gas system. So this is a Nash equilibrium a la Cournot, because we are using this kind of prices criteria. Observe that this is equivalent to solving the whole market clearing procedure. Okay, so anyway, just for simplicity, this is the kind of market structure that we are organizing. So now the ISO is somehow embedded over there. Is not the relevant thing. I'm considering individually every one of the producer in this case. I'm looking at producers here, but I can look at both producer and consumers at the same time. So this is the maximum profit that this pursue, but this particular gas producer 1, this is gas producer 2, they are interacting both of them through the price, the common price for both of them. Okay, which is the clearing of the market itself. The same thing happened with electricity, and what we get, the connection between the gas market over there, the red one, is the price of gas. The price of gas goes down because it's a constant in these two electricity problems, and what we get out of the two problems over here is the total quantity of gas that we need to produce electricity, which is in this case Q1G, Q2G, and this should be equal to the electricity which is allocated in the gas market to produce electricity, which is this 2 over here. Okay, so just a very simplified picture for to understand the interrelation between the thing. Okay, this is what we do. How can we solve this? Again, this is equilibrium. There is no hierarchy here. So we can write the KKT condition of the first gas producer, the KKT condition of the second gas producer. We can produce the KKT condition of the power producer 1, KKT condition of power producer 2, and solve all of them together. Okay? Yes? This one?
Yeah. And is it internal to the agent's optimization problems? It looks like in the previous slide that the power producers are the ones who...
I think the variables for this problem, I think the important thing, because we had to take derivative to take KKT condition, is to see which is the variable of what. And the variable, the variables of this problem is just, in this case, if G1E. So this constraint, we can put it outside if you want, or we can put it inside every one of the problem. It can be, we can write the KKT of this, the KKT of this, the KKT on this, the KKT on this, and then write this condition. Yes, yes, because they are telling us that basically all the gas that we get from the gas system is the gas that should be equal to the gas of the quantity that we're using in the electrical system. We have to explicitly say that, otherwise it may not be like that. And we may have equilibrium in which this is not the case. Yes?
Or you can add the extra optimization problem as price center. So.
Yes, whatever. We have many ways. So the only thing I want to say here is that they are interrelated. And they are interested through prices and quantities. And then we will see what we do in a more realistic case. We are not used Cournot. I don't like these kind of things because they are not realistic. This does not describe the way an electrical market. I think some of my very appreciated colleagues will disagree with me, but I don't think this is a good description of a gas and electrical market, even though it's the economic literature use these kind of things. But it's a very good way to understand which is the relationship between the different times. So I'm going to do things different. The only things I wanted to show is that this is the kind of thing that we do. So the equilibrium in this case will be the KKT condition of, in this particular simple example, of gas producing 1, KKT condition of gas producer 2, KKT condition of power producer that, a KKT condition of power producer 2. So yeah, they are interrelated. If we do equilibrium for gas by itself, or equilibrium by electrical by itself, why not combine all of them together and get a better picture of this? So this is what it is. And again, how we solve these problems, we stack together all the KKT condition and we can use an auxiliary problem. Well, this is a mixed complementarity problem, so we have a reliable solver that can deal with this kind of thing. If this is big, then that's fine. Otherwise, we can do the trick of using just maximizing whatever, subject to all these constraints. And since we have powerful solvers like Nitro or similar, that they can deal with this kind of problem, eventually we may be able to solve that. I mentioned now we are going to be a little bit more realistic. So for being more realistic, I'm excluding the collusion alternative. So I'm saying, well, for this kind of model, I have gas producers that sell gas. Okay? They just produce gas and sell gas, and they don't care about anything else. We have gas consumers that they consume gas. They buy gas, consume gas, they're happy, and that's it. Then we have power producers over here that they produce electricity, but they need some of the unit of this power producer, okay? They consume gas. They are combined cycle gas turbine. So they need to buy gas from the gas market. And this is one connection. So I'm just power producer. I don't care about gas, but I have to buy gas to produce with some of my units, which are combined cycle gas turbine. So this is a kind of agent that we are going to model. We are going to model an agent that need to buy gas in the gas market to produce with combined cycle gas turbine electricity to sell to the power market. Okay? Another thing that we are modeling is that, well, we have a power consumer, just consume power and that's it. Okay, and then we are going to model a gas producer that does both things. It just produces gas or power, and I can actually buy or sell gas depending on if I'm producing a lot of electricity and I need more gas than the gas that I'm producing. I can still buy extra gas for produce more electricity, and this is a good option. Okay. And then we have a gas power consumer. That is a facility, a large facility that may buy both things, may buy both electricity and gas for producing. Okay? So this is all the agents that I'm considering. I'm not considering, let's say, a gas producer that at the same time is a power consumer. Because that will be like, this kind of things. There is no... it will be much worse in the case that consider a power producer and power consumer at the same time. So, of course, I can produce an entity over here that produce power and consume power, and may try to be strategic in order to do that. I'm preventing these kind of things because typically this is not typically legal in many places, so you cannot be a producer and consumer at the same time, and to some extent, if you are tiny, then it's no problem, but if you're a co-generator, well, whatever. Anyway, that's the guy. We can extend that to make cross relationship between some of the agents as well, but okay. So, so in case of, we actually going to describe with some degree of precise, be precise in the description of this gas market and power market. So, and what we have to do is, in this case, the gas producer is going to produce, and this can be an stackable game. So this gas producer may want to bid to produce offer in such a way that is trying to modify the outcome of the gas market. So if this guy has actually, I'm not going to model in that in this particular case, but we can model, this gas producer may actually represent the clearing of the market to be able to actually represent in its own problem the modification of the prices as a result of my offers. I can do a stackable game here. Things became more complicated, so just for the sake of illustration in this case, we are considering all of them are competitive actually. So this guy is just producing offers, and the gas market, same thing for this producer that produce both gas and electricity. It may offer a bid, whatever they are, and it has a market clearing algorithm here that produce quantities and price. So this guy submit offer, this guy submit offer a bid, depending if it's wanted to actually sell or buy gas. And then this algorithm, this problem over here, clear the market that produce quantities for gas, quantities, in this case, for gas as well, and the prices of the gas, okay? And the same thing over here. So we have the power producer is submitting offers, the market cleared, and what they get is quantity and price. And we have this guy that does both things, with this interacting both of them. And again, the critical one, which is the power producer with a lot of gas, with combined cycle gas turbine that necessarily has to buy gas. So it's gonna actually send, in this case, those will be bid. So it should be a label here saying bid. This guy is bidding in the gas market to get gas and offering to sell electricity in the power market, okay? So this connection, this blue line over here, which is the more common, is the one linking heavily the gas and electricity market, that we increase the number of combined cycle gas turbine in the system. And this is the critical point in places like Spain, as I mentioned, or Texas, okay? Or may become a critical issue in the future, okay? So in the case of consumer, we are assuming here, again, we may produce stackable games here. This consumer may want to represent the gas market clearing in the problem that is used by this gas consumer to organize the bid to the market, and the purpose will be that the prices, the market clearing price, this price will be as low as possible. If I'm a consumer, I want to pay at least if I can. So in this case, I want to submit my bid in such a way that the price is the lowest possible one. So I can do that. We are not modeling that in this case, but we get things more complicated, but we can do that. Okay? The same thing with the power consumer. Power consumer, this is asymmetrical, right? Because the power consumer is just consuming power. There is no, as opposed to the case of the power producers that to produce electricity need gas. So this doesn't happen exactly at the consumer level, unless the consumer need both gas and power. But it's just buy the power, buy the gas, and that's it, okay? So this is the kind of structure that we are going to do. So let me be here very high level, and then I will be a little bit more precise. So the gas market clearing, which is this problem over here, the gas market clearing, is going to be a problem that somehow look like that. Gas is the variables of this problem. And it's actually maybe primal and dual variables. They are primal variables. It's the quantities of gas which is allocated to everyone offering into the market. And we have prices over here. So this price is related with the gas of price. Okay, and then the constant of this problem are basically the offer of bit. We're using A over here to refer to the offer of bit in this gas market. P is a variable which is constant over here because it's related with the power market. We may have interaction between the electrical and power markets, so this is why we have over here these variables. So we have problems that depend of the clearing quantities. This is the outcome of this problem, which is basically the quantities allocated to every producer, flow in the lines or the pipelines or whatever, and the data is A, which is the offer and bid that provide from the consumers or producers. And then instead of this problem, we just write the optimality condition of this problem. If this problem is linear, then the optimality condition is primal constraint, dual constraint, strong duality equality. Okay? And this optimality condition, again, depends on my variables, of the clearing variables, and other variables that depend on other problem. In this case, of the dual variables of this problem, P, which are the variables of the power market clearing, and lambda G, which is these dual variables over here. So the gas market clearing look a little bit like that. Again, we can produce here second order conic version of this problem, and this is the KKT condition of this problem. This is the optimality condition. There is a paper available that you can look in detail if you're interested. This is more optimality conditions, but we don't need to look at that. The power market clearing is the same thing. In this case, is the blue one. So the variables is going to be P over here. And then now the bid, I use B instead of A. So B are the offer bid that for this problem are constant. They are not variable of the problem, just the variables are the P and the dual variables lambda P and mu P. So for writing the KKT condition of the problem, the only variable of this problem are the P's, right? The vector P, and then the optimality condition for the power market clearings look like that. So has some constant in this problem, which are the G, which are related with the gas market, P, which are the variable specific of this problem, and then the dual variables, okay? And B are bid and offer related for other problems, not for the market clearing problem. Okay, so this is look like this is a pretty much simple thing. We are using here a linear version of the power market. Well, those are the optimality conditions. We don't want to look at that. And then, so we have now let me go back quickly. So what we have is for the market clearing problem. For the market clearing problem, we have the optimality conditions. It can be multi-period, single period. For the power market clearing, we have the optimality condition. So now we are going to look at the problem of every producer, of every consumer. Okay, so the problem of every producer. In this case, we are writing MPEC, because this is a problem with equilibrium constraints. It's a problem that inside the problem are the clearing of the market. This is the optimality condition representing the clearing of the gas market. Those are the optimality condition representing the clearing of the power market. And we are using those conditions. This is a band of equalities and inequalities, so I can put it there. Right? There's no problem with that. And I want to actually, my problem is that I need those variables because this variable describe the price. The price, this price over here, this price over here, the price of gas, the price of electricity, that I need to compute my objective function, which is going to be, I want to maximize my profit. If I'm a consumer, I want to minimize my cost of actually buying electricity. I'm being high level over here, but you have in the paper details if you want over here. So this is an interesting problem because we have whatever condition, this is the condition, equalities or inequality related with if I'm a producer, describing the operational limit of my production facilities. This is my profit that I want to maximize. And then I have the clearing of the gas market and the clearing of the power market, because I eventually may need either the gas price or the power price, okay? And then this is an optimization problem that inside this optimization problem we have optimality condition. This optimality condition might be KKT conditions, depending on the description that we do of the problem. And if you have a problem that inside have KKT conditions, these KKT conditions, they do not comply with nice regularity condition, which means basically if you remember, if we have a single optimization problem, if we want to apply the KKT conditions, the constraint of the problem has to satisfy some constraints, okay? Some regularity constraints. So we can show that this optimality condition, generally if they are KKT condition, they do not satisfy those constraints, okay? And then, so what we do then, basically say, well, in principle, we cannot take KKT condition, because I say, well, I have this problem now. I want to solve the equilibrium of many of those guys. This is producer consume L. I want all of them together. So I have this problem. One way to do that will be to write the KKT condition of this problem for every one of the consumer or producer. But I cannot write the KKT condition of this problem, because those conditions over here, they are not regular. Okay, well, for at least, not in general, but for very large kind of problems, the fact that these conditions are non-regular, what means is basically this KKT condition gives you stationary points, the standard points related to KKT condition, and a lot more points. So this condition, if those are not regular, you get more point than the point that you really get normally in this condition unregular, which is good. That means that you probably have to look more carefully, but I mean, it will be much more worse if this condition make the KKT conditions infeasible. Because in this case, you cannot do anything. If we apply KKT condition to this problem, what happens is that I get the regular points, well, not regular, the standard point that I get with using KKT condition in any, let's say, normal problem, and some other points. So if beside this complication, beside this complication, I decide to use the KKT conditions, it's okay, because they're going to get many points, which eventually I may get many points that they are not good in terms of equilibrium. But doesn't matter. I get as much as I can, and then I test using actually diagonalization to make sure that they are really equilibrium point. Okay? This is what we are going to do. So in this case, we use the KKT condition of this problem. This is how it looks like the MPEC, in this case, of a produce consume L. This objective function, I'm not going to go into detail, but include all the possible, yes?
So I couldn't follow how we got more points.
It's something that you can, if you look in detail at the KKT condition of a problem that inside the original problem has KKT condition, you can see that because of the non-regularity, the KKT conditions are more relaxed. So they are not more strict, they are more relaxed. So you are going to get the standard point and more points if you solve them. This is what happened. It's a fact. So to prove that, to be rigorous with that, there's a very interesting work of Professor Danny Ralph from the University of Cambridge, Danny Ralph, and he has worked on this. He was the pioneer, by the way, to do this kind of things. So anyway, it's a good situation, because I mean, you do not exclude anything. You get more things, so you have to be careful with the screening. This is what happened in general for many problems. So I'm not. So anyway, this is how it look like. This is a generic consumer producer. So we have an objective function with all the alternative here in the case that we need them. And then we have, this is basically the description of the bidding strategy. So those values are bidding variables or offering variables. And then we have the gas market optimality condition, power market optimality conditions, okay? So we need, again, over here, the consistency constraint that you were asking me. I can say the gas that I'm consuming, if I'm a producer of electricity and I need gas from the gas system, I have to be consistent. I mean, my equation has to say that the gas that I need, I get this gas from the gas system. And this is what it says here. So, and this, and you have to impose that with building the bid. So in other words, you have to, if you are, let's say, if you want to get gas to produce electricity, the way you bid, or the way you offer, the way you bid buying gas in the gas market should be in such a way that you get the gas. Because if you decide to bid very high, you may not get the gas. So we had to embed this within the equation, and this is embedded within the equation. We had to say explicitly that, I mean, the bid should be in such a way that I'm getting the gas that I need to produce electricity. This is what this equation say, basically, okay? And of course, if I impose those equations within the model I'm solving, then this happens, because it's solving the model together. So anyway, so what I have here is what we call equilibrium problem with equilibrium constraint, because we have many of those problems of this type, many problems of this type, one for every one of the producer-consumer, right? And we have all of them together. And and we call this an MPEC. And how we solve that? Again, the same trick. So we can use an auxiliary problem. We maximize wherever we want. And then we solve this KKT condition. Remember that this KKT condition provides us for all the producers of all the consumers. Just to mention that this gives us equilibrium point and many other things, because we don't have regularity inside the constraint of every one of the problem that has generated these KKT conditions. Okay? So, but instead of one, which is this one over here, we may use an appropriate objective function to pursue particular type of equilibrium. And this is what we do in this particular case. For instance, this is social welfare. We can use total profit of all the producers from selling electricity and natural gas. We can, another one, it might be the total utility of all the consumers that are actually buying electricity and natural gas. We can do any kind of combination because we have the two markets at the same time. And again, when we get solution out of this problem, if we get solution out of these problems, if we can, which is challenging in many respects, we should make sure that they are equilibrium, so we should confirm equilibrium via diagonalization, okay? So let me, in the paper you have, we analyze the Belgian system that I described previously with this type of modeling in an exactive way. You have details in the paper. But let me just show a very simple case in this case to see what happened, okay? So, okay, we have a gas system on the left, an electrical system on the right. So we have, this is a gas source, have here another gas source. We have two gas demands over here, another gas demand over here, okay? And then we have a gas demand which is actually supplied this unit, which is a power unit, but this gas-based unit. And this is not a gas-based unit. We have electrical demand over here, we have electrical demand over here. So we have a connection about this unit, and we may explore using this very simple example. We may have congestion in this transmission line. So, and we can see how electrical congestion in this system may transfer to the gas system. And on the other hand, we may have the gas system in this case, we may have congestion in this line or congestion in this line, in this pipeline or in this pipeline, and see what happened in terms of the electrical system as a result of congestion in the gas system. So this is the kind of analysis. Again, we did similar analysis in this case for the Belgian system. So we have a producer 1, which is over here. This is producer 1, which owns this unit 1, which is not related with the gas. So this producer 1 is not gas related, it's just producing electricity using whatever it is, coal or whatever, or hydro or whatever. And then we have a power gas producer 2 that owns, this is a power producer and gas producer, both things at the same time, and owns the gas-fired power unit 2, which is this one, which is based on gas, and then the natural gas source over here. So this is a hybrid type of producer that is interfering in the two gas. It can produce gas over here, and it can produce electricity over here. It's a particularly interesting position. So I'm a gas producer, but I decide to install power unit, combined cycle gas turbine, so I can combine my strategy between selling gas in the gas system and or selling electricity, converting the gas to electricity. And then finally we have a gas producer 3 that owns this gas source number 3 over here. That's it. So the only connection that we have here in this problem is this one. Okay. So we solve this problem using probably we use continuous formulation in this case. We are using Baron. Baron is a global optimizer. So, but this is not as fast as some other solvers. And probably the reason for using Baron in this case is that the problem is basically non-convex, non-linear, and you have to do whatever you done. So anyway, this is not a big problem, so we can solve and resolve and extra resolve this problem in many conditions. And this is basically the type of result that we get. So we use a competitive case. In this case means that we operate the whole system together. I mean competitive in the sense that there's no upper level problem. There is no strategy in terms of producing prices. We are just offering the actual marginal cost in this case. And you can see this is the result in terms of social welfare. If we solve the MPEC in which the different 3 producers, so this power producer 1 is producing offers to sell power to the best of his interest to maximize his profit, and this guy sell gas and electricity to maximize his own profit, and bid actually produce offered with this purpose, and the same thing for this one. And we do that. In this case, we have the MPEC, and the MPEC, if we maximize the social welfare, we get the same thing that the competitive one, which is a typical situation. So if we emphasize, on the other hand, the profit of the producers, in this case, all of them together, then we get a solution like this one. The social welfare is significantly smaller. And of course, the total profit of the problem is significantly higher. We can see that this number is significantly higher than this one over here. Okay? And then the case of a monopoly that we are just putting together all the supply resources to extract as much as possible money out of the consumers. In this case, because the consumer are not in this case are just competitive, they're buying whatever they get, then we get, well, in this case, is pretty much is exactly the same thing that when we maximize the profit of the producer. So this is a typical situation. If we solve the MPEC with social welfare, in this case probably is the same because it's a very tiny example, but if we have a more sophisticated example, we may get solutions here which are close to competitive, and if we do that, we get solution which is close to the monopoly case. Okay, so that's the typical thing. Let's see what we are doing here. Okay, this is different equilibrium. In this case, we have different equilibrium in this case. So, well, in this case, the objective is the profit. So we are in the same case that this. We are in this case over here, but we restart bound in many points, and we get different equilibrium points. So the equilibrium is not unique. We can clearly see that. Okay, all of them are equilibrium. So we are, I guess that Shen did that, which is to verify that each one of those points are indeed an equilibrium using a diagonalization. So I fix the actual actions of producer 1 and 2, solve for producer 3, and get something, fix that, and then fix that on producer 1, and solve for producer 2, and get something for producer 2, and then I fix 2 and 3, and solve for producer 1, and nothing changed. So this is an equilibrium, and this is all of those should have passed this test, and those equilibrium as well. You know, they are not very different in terms of social welfare, but in terms of the profit of different producers are somehow different. So that is a typical situation as well. So we want to identify all these kind of things to see. Okay. Then what we do is to congest this line over here. So we are making difficult for this producer over here to actually sell electricity over here. Okay. And if we do that, we can see 15, 10, and 7. So we are reducing progressively the capacity of this transmission line. We can see that the profit of this producer over here, which is the only non-gas electricity producing facility over here, we can see that the profit goes dramatically down. Basically, we don't allow this guy to sell much, so, and this is what happened. And well, in this case, it's pretty obvious. So if we congest this line or reduce the capacity of this line, we clearly are getting trouble into this one, but these kind of things may happen in a huge system, and it's not easy to identify. So this kind of congestion might have very significant impact on particular areas of producer, and this is not, this case is pretty straightforward because of the simplicity of the network, but in other cases cannot be, it may be very different in this case. You can see we are not significantly change the social welfare, we are not significant change the total profit, pretty much the same. This is pretty much the same, but this guy is getting down very significantly with respect to the other two. Basically, is the second one is we transfer income from 1 to 2 by congesting this line, which makes sense in this very simple example. Yes, please.
In case of this multiplicity or having multiple equilibria, does it make sense to do some stability analysis to see how resistive they are or how robust they are with respect to any small perturbation?
I think so, yeah. So yes, yeah, very, I think, well, in the particular case of this multiple equilibrium case, In any other case, we want to do a stability, sensitivity analysis of everything. So this is always a very good idea for any kind of analysis. If you do an analysis, later on you discover that this is extremely sensitive to the resistance, well, not resistance, the reactance of a particular line, you want to explore that. That might be the result of not very good formulation of the problem, maybe the result of the structure of the problem, but you want to analyze all type of sensitivity and stability. I would say all the parameters of the problem with respect to what you get.
And I suppose they are not equally sensitive.
No, exactly. So you are right. Okay. So anyway, so if you are, for instance, what we can learn from here is, let's go over here. Again, this is not, I don't use that to offer in the market. If I'm a producer number one, I don't use this equilibrium model of everybody to identify which is the best way I want to actually offer in the market. I don't do that because I need the information of everything and I don't have this information. Well, I may try to do that anyway, but it may be approximate. But what I can certainly do a model of this type is to say, well, I should be careful that this line does not get congested. Because if this happens, this is bad for me and good for this guy. So I should prevent that. I should try to identify that. I should fight, try to combine the ISO, try to combine the regulator to make sure that this doesn't happen, because otherwise I'm out of business. And in this case, pretty obvious. In large cases, it's not obvious at all. So the action that you may want to pursue, which are good for you, they are not probably straightforward or easy in this particular case. Okay? Okay, so let's, yes, you have, yes, please.
Why don't we consider a gas producer as power consumer?
Yeah, we can do that. So the only thing, let's go to the beginning over here. So, is this one that you're referring to? This is a power producer, is a gas consumer. So because it's actually extracting gas from the gas market. So this kind of entity is actually a consumer for the gas market and a producer for the electricity market.
I think we need also another connection between power consumer and gas producer. I mean, to produce gas, we also need electricity, right?
Yeah, well, we can do that. Yeah, if this is a significant, component of the gas consumption, yes. So if it is a small part of the total, let's say, of the total volume of business in terms of quantity, yeah, if it is relevant, of course, these gas producers, you mean, need electricity, so it has to be connected to that. Yeah, if this is relevant, we can model that with no problem in this kind of setting, yeah. What I wanted to emphasize is that we don't want to have a gas producer and gas consumer as a single entity, because this is typically the law in many places. You cannot do that. You cannot be consumer and producer at the same time, because you manipulate the market, basically. You are in a very good position to manipulate the market if this is the case, okay? So, but yes, so if this gas producer really needs a significant amount of electricity to actually produce gas, then why not? Let's cross this line over here. Yeah, thank you.
Sorry, Anthony. I see your point that consumer and producer, they should not be the same, but I see that you are talking about the wholesale market, but in local market, we have the push.
Yes.
Part of our future.
Yes. No,
So
right. Well, I think we have this framework for the more general wholesale market. But I mean, if we have a bunch of BPPs, and let's say that we have a distribution system which is large enough, this island, with a lot of BPPs, we can build some framework similar to this one, and in this case, we don't have this collusion type of things. So any kind of those entity can be producing or consuming at the same time. But yes, perfect. And the framework doesn't change. That's true.
Also, like big storage units, even like if it is not local and small, but big storage unit also. Right?
Yes.
Produces
Yes. So particularly the simple, there's a very interesting case which is would fit into this problem is that we are looking at it. Actually, let's say that we have a distribution system operator in this, in this island, for instance. And then we have some clever consumers that they have a solar system. Let's say a solar and wind system. Let's make it more complicated. This is solar, and then this guy has a significant battery over here, and then has a consumption. Well, it might be a small factory, or it might be you're very sophisticated. Then we have a single computer here, and we decided that this is the variable that can be in both directions. This is the power of, let's say, the independent consumer. I just buy or sell, and I have a simple algorithm here. At some point, we will have, the network will be over there, and it will be a connection to the DSO, and it will be a price here to extract power from the network, maybe bidirectional. So the price is bidirectional in those things. So the price and how translate here, the translation is not straightforward, but it's clear, and we may have many guys of this one. So they are prosumers, and they control this connection. So I'm the one who decided how much I extract, how much I actually inject. And then we have some kind of coordinating entity here that we can model. It's clear, let's say that this coordinating entity is trying to maximize, social welfare for the DSO. But clearly this guy is trying to maximize his own profit, maximum profit, or minimum cost. So I can use my solar and wind resources and my battery to try to produce or consume the least I can. If the price is very high, I don't want to buy anything. Well, it depends. I also have a temporal connection here. The storage don't allow me to do everything a single hour, so I have to model a whole day over here. So, and this is clearly an equilibrium in that problem. So this problem is, let's say, is maximizing, let's say, profit. And this profit clearly depends on this variable PIC, which is the PIC is the variable of this problem. And it depends of a constant, which is the lambda, this price over here translated over here. Let's call lambda translated, because we going through the DSO, the price may be different for whatever reason, okay? So this is a problem, and this is subject to the constraint related to the solar, wind, storage, and demand, my own demand, okay? And the problem of the DSO will be a different one. And the problem of the ISO, let's say, is going to be maximize social welfare or whatever that depends. And the variables of this problem, let's call it X. And this objective function depends of X, of course, and depend of some constant, and one of the constants is this PIC, which is not a variable for this problem. This guy is not deciding on this variable, but it's a variable of the problem, so they connect both together. So this is subject to whatever constraint, let's say constraint of, let's say, DSO, that depend of X and also PIC. Okay, so we have to solve this problem together. This is an equilibrium, clearly. So to describe what is going on, in a system of this type, we have to solve this collection of optimization problems. This is not equivalent to a single optimization problem. In my view, it is not. Because, I mean, this guy pursues an objective. I pursue a different one. And this is the basic condition for not having a single optimization problem corresponding to both of them. So if my objective is not aligned with this objective, and my profit is nothing to do with the social welfare of the whole network, okay? Then I don't have a single optimization problem that represents this situation. This is the basic condition that I probably should have mentioned previously, which is in the previous problem, in the gas problem, the gas system was, the previous presentation, not this one, the gas system was trying to minimize cost of gas. The electrical system was trying to minimize cost of electricity. Both costs, they are both aligned. So this is why we have a single optimization problem. Over here, they are not aligned. The profit of this guy has not necessarily has anything to do with the social welfare of the DSO. Just please let me know, because I know you are interested in this.
I'm not sure I see the point, because the social welfare maximization of DSO, in this case, you have one lambda, we're assuming one lambda, right? Which is basically uniform pricing, which by perfect computation assumes that the maximization of social welfare of each of the agent correspond to the social.
No, there's no need to perfect competition here. This is our first thing.
If we assume a constant pricing is the same, right? Like a lambda that comes from this infinity grid, which is a constant.
No. I mean, if you, the best for the DSO will be to combine this guy to produce or to use the storage and the wind and the solar to minimize the cost of the whole system.
Right.
So I don't want to do that. You are telling me use the gas, my gas that I bought myself and installed myself and pay the installation for it.
But
both this.
Go up and incentivize those agents, right? And then the equilibrium is what the price provides enough incentives to the agents to actually participate and see that as profitable. And if they don't see it as profitable, it's not maximizing social welfare.
No, I don't think that's the case. Well, but look at this problem. So I just operate that for my own benefit.
Right.
This is different than operating it in such a way that it benefits everybody else in the system. This is clearly different.
I don't know. The problem is that if the system is perfectly competitive, then maximizing social welfare is equivalent to maximizing profit of everybody. They're equivalent.
Yes.
So if this prosumer is perfectly competitive and we combine
But I don't want to do that. I don't think that's not the case. You are gonna, of course, you are gonna do whatever you have a computer here to try to be clever, to try to maximize yourself without try to modify whatever you want. If you want, yes, of course. Yeah. But otherwise, it doesn't make. Otherwise, I don't think it's connected with the real world. See, the real world is, yeah. Okay, so I think we have not a lot of time for the last part. Something else over here, perhaps some conclusions. So this is a multiple leader to follower problems. Multiple leaders, everyone wants to be a leader. Everyone has to be strategic. Everyone has to modify prices. So I don't think there is no, let's say, perfectly competitive guys. I haven't seen any one of them in all my history with the power industry. So the power industry, they want to change prices, to change everything to their own benefit. That's the purpose of, even if you're tiny and you're influence no one, but you really want to be big. So that's what is happening. So anyway, this is the structure that we have, and so multiple leaders, 2 followers. This is a double Stackelberg game. If you want to look many leaders and then two lower level problems to follow, which are actually there's a very interesting work related of this interesting work from Professor Leifert on this type of analysis, which is a very one. And we can use this kind of model to understand which is the impact of network congestion of hybrid firms if we are, for instance, owners of electricity unit that need gas to produce, but at the same time we own gas sources, which are the effect of this hybrid, this kind of horizontal integration, which are the consequences of the market as a result of horizontal integration. And then we may have, in this case, I didn't look at the problem in which the demand is also exercising market power. It's trying to beat in the market in such a way that is altering things, okay? That will, but anyway, the framework is pretty much the same, so anyway. So one interesting thing that I did over this analysis, I assumed that electric and natural gas LMPs are transferred from the gas to electricity at the same time. So I assume, like I didn't do in the previous presentation, that there's perfect coordination between gas and electricity market. If this is not the case, this became even more fun. So if we aggregate the price of gas to transfer to electricity system, what happened? Which are the consequences of that in this type of framework that we are building here? Okay, and this is the paper. I think you can, if you look at the webpage of Professor Hansi is over there, or you can actually ask me for the paper if you want. Okay, so we have not a lot of time, but I think we have time for, unless you have questions, that I think this is more important. Any question of observation? No. Well, we can extend what we did to investment models. Again, this is work with Shenshen and my colleague Francis Hansi. And so a little bit over here, we can extend the type of model to investments. So the problem that we have previously is operational model. So if I have to make an investment, what I have to do is the same kind of thing, but consider not just one operating condition, but many operating conditions. As many operating conditions at the life of my machine, if I build a combined cycle gas turbine that lasts 20 years, so I have to represent what happened the 20 years. So if I represent what happened the 20 years, maybe I have trouble with the computational model, right? But I can try to represent this future in a compact way as a number of operating conditions, okay? And we can use this kind of model to understand which is the investment equilibrium. In this case, perhaps it's a good idea to look at projection of different, in this case, again, the Energy Information Administration, and we can see that projection to 2050, we can see that the projection that this agency is projecting for the case of US, there is no coal, that's very good, no nuclear, sounds good as well, and we have gas over here, and gas, wind, and solar, mostly solar and gas, okay? So some other stuff over there. Anyway, gas, again, is playing a very fundamental role. It seems to be every agency is thinking that. So if I'm a producer and I want to invest in a gas unit, which kind of model can I use? Well, we can extend the operational model that we have described previously in the case for investment. And in this case, I'm going to do this thing using the same kind of thing with emphasis. So the kind of analysis that I'm going to do is the only alternative for building is a combined cycle gas unit. But we have many producers, they compete building those units. I won't consider that they built only those units, just to emphasize the connection between the gas and electricity markets. So it's an investment analysis in which we can only build combined cycle gas units that interacted to market, and this is why I want to look what happened in these cases. So, and again, we have a Stackelberg in this case with two followers, the gas market and the power market. This is electricity market clearing, gas market clearing. We have, we need a number of operating conditions. So this is an investment problem. So I don't want an operating condition. I need as many operating conditions, as many days, representing the 20 years into the future that my investment is going to be alive. Okay, and this is the same thing for the gas market. And then we have producers like this one that is only interact with the electrical market, this one which only interact with the gas market. And then we have producers that they interact with both electricity and gas market because of the again, they use combined cycle gas turbine, they invest in new combined cycle gas turbine, they need to buy the gas to actually produce electricity. So we consider only investment in combined cycle gas turbine. Actually, if you look to the Europe and US, and only this kind of unit has been built in the last, 10 years. Of course, renewables and these units, no other type of units. So we might be a good idea to look at this unit. This is a partial look at the problem, but what we are looking in very detail over here is, well, which is the impact of building those units, which is the competition of different agents building those units in a particular setting in the network, right? Okay, so again, now we have different operating conditions. So this is gas market clearing operating condition T. Many of them, so this is a problem like the gas clearing that we have previously, but for just one particular time period, the gas clearing. So this look like that. This power clearing a particular time period, like this one. And then this look like that in reality. And then this is the same MPEC that we built for the operational problem, but then we have here investment variables, so we can invest, and then we have market clearing condition, not just for the single operating condition that we have previously, for all of the operating condition. And for all the operating condition, gas market clearing at the same time. This problem is non-linear, it's non-convex, and again, we have the same condition because of these typically are KKT condition. They are non-regular constraint, and this produce the problem that I say, that if we take the KKT condition of this problem that we get, we identify stationary points and more points in addition to those ones. So this is how look like the upper level problem in this case, and this way. So the producer MPEC is going to be like that. This is the profit for this MPEC, upper level constraint related with the actual building of the unit, and then primal constraint, because the problem is linear, so primal constraint for primal constraint, dual constraint, and stone duality for the power problem for all time period. And this the same thing for all time period, 1 to t, all of them, okay, for the gas. And this is, we call that KKT L, because it's the KKT of producer L. The time periods are all of them embedded over there. They are critically important because we have to describe the whole life of the facility, okay? And so this is the KKT condition, and we want to solve them together for all the producers that they are competing. Again, gas power consistency, the gas that we use for electricity production has to be obtained from the gas system, so we have to embed this kind of thing inside there. And so we solve this MPEC is just similar to the other one, but much bigger, because we have many operating conditions inside, and we have new variables, which are the investment variables. So I think just look at this simple example that we have over here. So we have, again, we analyze very detailed the Belgian system as well. So you can look at the paper for that. But anyway, that's the system that we have. This is the gas system. We have 4 nodes. Okay, we have a gas source here, another gas source here, 3 gas demand, and we have a demand for gas to produce electricity. We have electricity production here, and this is electricity production as well of a combined cycle gas turbine, and another one over here. Electrical demand over here, 2 lines in the electrical system. So the coupling between the gas and the power system, including this unit over here, this unit over here, and this unit over here, okay? That we're using gas to produce that one, okay? We have another unit over here that is not using gas. And and we have 3 producers in this case. So the blue producer is number 1, which owns an existing power unit over here, which is this one. And it may build a unit over here, which is this one. This is a potential combined cycle gas turbine that can use gas from here and operate ingest power over here. Okay. Producer 2, so this producer is just electrical one. Producer 2 owns gas-fired unit 2, which is this one over here. Candidate gas-fired number 2, which is this one, is the candidate, and this gas source. So this is a hybrid one. The number 2 is the interesting one because it's the one actually linking very heavily the 2 systems. And then we have power producer number 3 over here, which has a gas source over here, which is injecting power over there. So this is the architecture of this simple example. And well, there's some data over here. I represent in this very simple example just 3 operating conditions. Each one corresponding to this number of hours of the year. Of course, we need more than 3, but just for simplicity, we have some data on the problem, and let me see the type of solution that we get. So this is the investment result for the case in which we are decreasing the power interconnection. Let me see, okay. So this is the system we are decreasing the power in this line, the power capacity of the line 2 to 3. And if this happens, this is the result that we get. So we can see that the social welfare change as we reduce the capacity of the line. It goes down all the time, which makes sense. And in terms of the capacity that the new capacity that we built, we can see that this is decreasing actually, and unit 2 is, well, it's a not trivial pattern which is happening here. It goes down and suddenly it goes up, and it goes down and then goes up and goes down. So it's very it's kind of interesting behavior which happened here. So those are the investment result, and result relating with prices that we reduce the electrical capacity of the line, price goes up. This is the electrical price in the 4 node. So this is for time period 1, time period 3. Time period 3 is the same. They do not change, operating condition 1 or 2. So, but we can see that as the line gets more congested, price goes up. And this effect on price may be beneficial or not for further investment in one particular area versus the other. And okay, so there is some explanations here. And this is the gas prices, and we can see that the gas price changed significantly. Well, to some extent, they change as a result of the transmission capacity of the electrical line. So the electrical line is influencing as well what happened in the gas system because of the interconnection. And well, I think this is it. We have 5 minutes for final questions. So I went a little bit fast in this particular part, but this pretty much the same as the other one. But yes, please.
So I
Yeah.
It expands quite fast when we are increasing the number of
Yeah,
time,
yeah.
the number of nodes.
Yeah.
And then sometimes it's really hard to get solution out.
Yeah, I agree. Yes. So the problem do not include binary variables. So we don't not linearize. They are continuous problems, but big enough. I would say we have to be below 100,000 variables.
Just one. Okay, all these problems have been remained non-linear.
Yeah, yes. No, I don't think we did linearization. I don't think is as soon as you include the gas, if you are only with electrical stuff, then you can linearize many things. As soon as you incorporate the gas.
Okay, but what about the solution quality? Really, we can be optimal?
Well, no. I mean, if you have a non-convex problem, you have security of nothing. That is, life is as hard as that. But well, we did a lot of analysis, restart the algorithms. We will do all the, let's say, security checking for try to make sure that those solutions are the best that we can. Sensitivity analysis, restarting in different starting point, using different solvers. In some very tiny cases like that one, you can even use full enumeration of the cases because we are in. Actually, if you had if you have continuous options for investment, not, but you can use a step of 1 megawatt. And do even full enumeration in this case over a range of the kind of things that you do. So we did all the kind of safety checking that we could, and those are the results that we get out of that. So it's, but I mean, yes, my experience for the state of the art, as I see it, as soon as you introduce gas equations, the traditional, Jalal did very clever things in his PhD works some time ago, a long time ago, to linearize electrical system. I don't think we can do that in gas system. Things became much more tricky in that sense because, I mean, always that we have a nonlinear thing, we can try to linearize either because of the KKT condition, they have a quality constraint, we can use that to try to identify things to eliminate the nonlinearities. We can try to, even though since we have, we can even fix some of the variables of the KKT condition, the final KKT condition, to constant valued, and these do not originate an infeasible KKT set of KKT conditions. So
with the linearization also that it's always introducing either binary variables or increasing the number of constant
right.
Again, expanding the problem.
Okay, of course. But simplex is very good and Gurobi as well. So we can even very big problems. We can if they are linearized, if they have binary variables, we have a good chance to get some kind of solutions. If we use decomposition on top of that, maybe But so far, we have limited experience. We have been working on this for say a couple of years, 3 years, this type of models. But my experience is that we couldn't find good ways to linearize gas equations. They are deterministic model in the sense that we are using many operating conditions, so they are not deterministic in the sense that the shorter uncertainty is described. Because, we are describing different days, and different days mean different demands pattern, different correlation between the, let's say, if we have wind, there's not wind here, but all kind of, the different days represent the shorter uncertainty. We didn't describe here anything like, but anyway, but also we didn't describe that the demand is growing all the time. So that will make things significantly even more complicated for that, yeah. Sure.
Thank you,
So,
Antonio, for this post.
yeah. Thank you.